Hi everybody, lecture 29, 29A if we want to be specific. Last lecture of PH 112 online. Yay, thank you for your attention to all of this. Thank you for putting up with everything. Hope you're doing okay, hope you're safe. Last lecture, there'll be a 29B, which is the applet version of this thing, but that'll be it then. So, converging lenses. Converging lens. Here's a converging lens. A converging lens is a piece of glass or quartz or some kind of optical material that has this shape if it's a converging lens. It has a concavity if it's a diverging lens. So here's a converging lens, and if I take a ray that comes into the lens parallel to the axis of this lens, it will bend in such a way that it goes through a point on the axis at the distance of the focal length. Here's the midplane of the lens, and here's the focal length right there. Okay. To find an image by ray tracing, we only need two rays. Okay. We only need two of these guys. We use three or sometimes four, but we only need two. Here's another ray that we could use, and I'm giving the lecture basically. If there's a corresponding focal length on this side, the conjugate, so I'm drawing an object sitting here. Here's my canonical arrow sitting there. Somewhere the top of that arrow tip is going to be along this line here. I need to intersect one other ray to know where it is. So if I take a ray that goes through the focal point, this one, the conjugate focal point, F prime, it hits the lens here and goes out parallel, okay? So where those two rays intersect, that's where the image is. So the image is here. Let's characterize that image. What can we say about that image? That image is inverted. It's upside down. Here's the top. Here's the top. It's a real image because if I put a piece of paper there, I could actually project it. I could see it. The rays actually go through that point. So it's a real image. It's inverted. And the magnification looks like it's about 1. Or I should really say that's -1. The minus sign means it's inverted. Okay, so that's only two rays. I could pick a third ray. I could pick a ray that goes through the very center of the lens. By symmetry, it'll go through the lens unchanged, so it'll go through there. Okay, but I don't need all three of those rays. I need only any two of those. Okay. All right. Well, here I just said most of what's on this page here. Here's a converging lens, focal length on this side over here. Here's a diverging lens. A diverging lens has this concave shape, at least on one side, okay? And if you look at the double bends of this thing, your author will tell you a little more about this. This is called the lens equation. I don't normally talk about the lens equation very much, even if we're back in the old days of in class. But if I make the glass bend that way, I get a diverging lens. Then a ray coming in parallel goes through the focal point. Oh yeah? Well, what do I mean by that? Here's what I mean by it. Here's a ray that goes that way. It's going to bend out that way, okay? And all these rays diverge. But if I take the projection back to that point, here's a ray coming down here that goes that way. All of those rays converge at a focal point, which is on this side of the lens. In today's lecture, we're just going to talk about converging lenses. So here, we're going to do ray tracing for a converging lens. And spoiler alert, here's the answer. Here's the answer. It says that 1 over the object distance plus 1 over the image distance is 1 over the focal length. That's the lens equation, right? It's exactly the same as the mirror equation that we did previous lectures, 2 lectures ago, okay? Here's what we're going to do for our diverging lens. Spoiler alert. It's going to be exactly that same equation, except it'll have an algebraic sign difference, okay? It'll say that dO plus 1 over di with a minus sign is that, plus it's 1 over the focal length, but there's a minus sign there, okay? Those two equations are the same, okay? Except that for a diverging lens, we replace the focal length with minus the focal length and the image distance with minus the image distance, okay? Everything else is the same. The magnification, in terms of the heights or the distances and so on. Okay. Look, I'm going to do this one more time in a little bit more detail than before. Here's the picture for image formation of a convex converging lens. Here's an object which has a height h0. Okay. Here's the image over here, which happens to be inverted and real. Okay. Ray coming in parallel goes to the focal point. A ray going through the focal point comes out parallel. A ray through the center goes through straight. Okay. I get two sets of similar triangles. This triangle is a similar triangle to that triangle. Okay. There's another pair of similar triangles. HO over DO, that's this triangle here, and this one down here, this bigger one sitting here. Okay. For the first pair of triangles, from the geometry, I get HI over HO is that. From that second set of similar triangles, I get this result. Solve those two equations together, get some algebra going, and you get the lens equation. Okay. You get the exact same result for a diverging lens. A diverging lens has a ray that comes in parallel to the axis, goes through the focal point. Well, no, it doesn't go through the focal point, but its projection does. Okay, the ray goes that way, but if I extrapolate backwards to here, it goes that way. Okay, here's a ray that comes out that way. It comes back on itself. So those two rays alone define this. Okay, so again, I have here's the focal length, here's the object distance, here's the image distance right here. So this triangle is similar to that triangle, and so on. If you do all of that and this similar triangle, you get that result there. Okay, I've already told you that. Well, look, ladies and gentlemen, that's this last page. Oh, one last thing here, since a lot of you are going to be in the medical business. I just mentioned this, and like me, many of you wear glasses. Okay, many of you wear glasses, and the question is, when you go to the optometrist or your ophthalmologist, as I do because I've got chronic dry eye syndrome, the disease of my generation, they talk about the strength of your eyeglasses in a unit called the diopter. Okay, what's that magic all about? Okay, it's just another way of talking about the focal length of the lenses that you use to correct for your eyes. A diopter, the definition of a diopter is 1 over the focal length, except you got to be careful because this is an engineering equation. It's an engineering equation because that focal length has to be expressed in meters, not in centimeters, not in inches, whatever, how many meters it is. If I put the focal length in here, take 1 over the focal length in meters, that's the lens power, P, lens power, P, in diopters. Okay, so for example, if you have if the lens you need has a focal length of 20 centimeters, you can't put 20 centimeters in, you put 0.2 meters, so you have a 5 diopter lens. Okay, that's the last page of the last lecture in Physics 112 online. Adios, mis amigos, mes amis.